This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus. It's episode 769. This week we welcome Dr. Dustin Poppendieck to talk about methods for evaluating air cleaning technologies. Air cleaning technologies can be complicated. It's hard to know who you can trust, but there are now some better standards and guidelines to help with evaluating the claims of manufacturers and others. IAQ Radio's marquee sponsor is the Institute for Inspection, Cleaning, and Restoration Certification, IICRC, a nonprofit standards development and certifying body for the cleaning and restoration industry at IICRC.org. IAQ Radio Association sponsors are the Restoration Industry Association, RIA, at restorationindustry.org. The Environmental Information Association, EIA, at EIA-USA.org. IAQ Radio industry sponsors are Particles Plus at particlesplus.com. Tramex Meters at tramexmeters.com. EMSL Analytical Inc. at emsl.com.
And now you can win a cool prize. It's time for the IAQ Radio Trivia question. Be the first to correctly answer. Simply email your answer to czlotnick at cs.com. Or if listening live, just text your answer from your computer. And now, here's the Z-Man.
Hello, everyone. Here's today's IAQ Radio Trivia question. In what year did the United States government adopt a uniform set of standards for weights and measures? Back to you, Joe.
Okay, Dr. Dustin Poppendieck is an environmental engineer at the National Institute of Standards and Technology. He received his PhD in civil and environmental engineering from the University of Texas at Austin. He is a fellow of the International Society for Indoor Air Quality and Climate, and recently he's been involved in writing and revising standards related to chemistry of portable air cleaners. Welcome back to the show. We had you not too long, well, maybe it was a few years ago now, with a couple other folks. I think we were talking about ASHRAE 241 maybe then.
I don't recall exactly the topic, but yeah, it was a couple of years ago.
Let's start real quick about your background at NIST. You know, what all are you doing there, and how? I guess before that, I noticed you were at UT Austin, and I wouldn't be surprised if I met you down there many years ago. You were with Rich Coursey and his group, and who today is kind of taking the mantle? UT Austin, you know, trained all those PhDs, got all these people in the IEQ world. Are they still doing that?
That's an interesting question. If you look at the indoor air quality research field, it's changed quite a bit in the last decade or two. Definitely in the 2000s, the University of Texas Austin was one of the, it was actually after I left, became one of the premier places for indoor air quality research. But since that time, a couple major things have happened. There's been a lot of really fantastic research coming out of China, and some of the interesting advances, and definitely some of the modeling side. Seen a lot of work coming from Tsinghua University and people who were related to Tsinghua University. But also in the last probably 8 years, there's been an influx of people from outdoor air coming into the indoor field. And so we have a lot of people who are trained from very high levels of analytical chemistry, knowing great chemistry, coming from their knowledge base and moving into the indoor field. So people like Delphine Farmer at Colorado State University has done some fantastic work. We also have Alan Goenstein, University of Toronto, blanking right now. But that's some of the, sorry?
Jeff Siegel, I think, was
Jeff
up
Siegel's
there.
up there, but also, so Jeff Siegel combined with John Abbott,
okay,
chemist up there, are doing some great work. But then also the people who graduated from the University of Texas have migrated out and become the stars of themselves. So you have Michael Waring at Drexel, you have Brett Stevens at Illinois Technical Institute, something like that. And some of the other peers of that group have established great research efforts in the last few years.
Well, tell our audience a little bit about what you're doing at NIST these days.
These days or in the past? Which?
Well, let's look at today.
Okay, so today, I would say, like, in the last 5 years, what primarily we've been working on in the indoor air quality and ventilation group within the engineering laboratory of NIST, our research has primarily been focused on, well, in general, what we do is we try and look at emissions and chemistry related to indoor air chemistry. So historically, the things that we've looked at are things like emissions from polyurethane spray foam, looking at both like the flame retardants that come off of them and all the byproducts that may come off when you have a bad spray. And so trying to quantify that chemistry with we've developed test methods. We've worked with FDA and looked at emissions from cigarette butts to try and quantify life cycle assessments. And you can get this, just side note, you get the same amount of nicotine from an extinguished cigarette butt over a week time frame as you do if you were in the room when the person smoked it as secondhand exposure. We've also done fundamental chemistry. And so in the last 3 years ago, or is it 4 years ago now, we invited a bunch of those researchers I just mentioned to our residential test facility here on campus and did some fundamental research looking at a wide variety of indoor air chemistry related to acid-base chemistry, cooking emissions, how low-cost sensors perform, tracking, radionuclide trace ozone and seeing how that ozone moves throughout the chemistry chain in a house all the way to positive surfaces, and then of course air cleaners. And that led us to my primary emphasis these days in my personal work is looking at how do we quantify the chemistry related to indoor air cleaners. And that's what we've been focused on most recently.
I noticed next week, I don't know if it's a NIST seminar or conference or if it's a National Academy of Sciences, they're doing something on indoor air next week. Are you part of that?
Not that one specifically. I've been involved in several of the National Academy indoor air efforts, primarily related to what we did with the fundamental research from the group that did the chemical assessment of surface and air quality.
Yeah, this is the chemistry of indoor air. I'll put it out with the blog so that people can.
I was involved in the NASEM report on. I was one of the authors on the NASEM report for why indoor chemistry matters. Yep. And that report, along with some of the particle reports, they periodically have various NISM events in DC about that.
All right, let's move on to the air cleaners a little bit. Why all the interest in air cleaners right now? I guess I kind of have an idea, but from your perspective.
Well, the short answer is money. The long answer is why is the interest. I mean, it really goes back to a combination of two major events that have happened One being, of course, COVID-19, and people trying to figure out what's the best way to we get society back to acting normal, and then also the wildfire events and WUI events that have happened to a greater extent in recent timeframes. But one of the big drivers, though, was the big Canadian wildfires in 2023 impacted the East Coast. And so now we have this, the mega city in the US that 100 million people live on the East Coast suddenly had bad air quality for a week and a half. And, we had air quality indexes above 350 outdoors. And people were like, hey, how do I prevent this from impacting my health? I have a visual representation of bad air quality when we have these wildfire events. And so because of that, we have an increased awareness of the impacts of indoor air quality can have on our health when we, see the air quality deteriorating before our eyes, and then we have respiratory issues. We make that fundamental connection between there's something in the air and I need to take some action. And so, we have schools and parents who really want their, to operate, whether it be in a pandemic recovery mode or, just to make sure that we're not being exposed to wildfire smoke, willing to try anything to keep schools open. And so, air cleaners became part of a multi-tiered approach where we have, more ventilation, we have fewer people in spaces if we're worried about biological risk, or we increase our air cleaning capabilities, whether that be in a duct or in a portable device that you have within the room. And because of that, we have this bigger market. And so we have more people saying, hey, there's a more demand. And whenever you have more demand, there's going to be a supply that rises to meet that. And so we have a lot of, in the last 5 years, a lot more companies have come to this, air cleaning space, and they need to differentiate themselves. And so we have, trying to keep, different companies are claiming they have the new latest and greatest technology to clean airs. And we have new technology combinations of these, really what they are new combinations of old technologies.
Okay.
We're putting the Legos together in different ways and calling it a different instrument. I mean, a different technology, but they're just different ways to put the Legos together that and these new companies are using to try and differentiate themselves in this space. And so what's happened is that we realized that as we have all these different assemblies of the Legos coming to the space, we didn't necessarily have standards that we could evaluate the claims that some of these companies are making. How their technology works, is it better than other technologies, or what's on. And there was, over the last several years, there have been several lawsuits where people have said, either your technology didn't work or your technology is harmful. And there have been various tests that were used to support or refute those allegations within the legal community that were not, let's just say they were not consensus tests to support the claims. And so there was this demand that, as we get to those new technologies, for a level playing field, companies in the market want to have a playing field that's level. They don't want somebody to make a false claim and be able to benefit financially from that false claim. So there's a demand to have a level playing field. And so we need new standards so that when we have this surging interest and the surging demand, that we have standards that can basically make sure everyone's playing the same game.
And NIST isn't necessarily developing these standards, but they're collaborating with other groups, and that's how you've gotten involved in this?
Correct. So it's important to note, NIST is not a regulatory agency. We don't have the power to regulate anybody. Where we make our impact, we're part of the Department of Commerce. We're trying to increase I should know Department of Commerce goals better than I do in NIST goals. We want to, increase people's well-being while creating a vibrant, healthy marketplace. And so our goal is to make sure that we have standards that are leveling the playing field, everybody's playing fair, and that we do it in a manner that's safe.
Well, let's go through a couple of these standards that you've been helping with here, and we'll start with the ASTM D8625 2025. So I guess that's pretty new. Standard test method for chemical assessment of air cleaning technology. So you're developing a standard test method, and this is to determine the chemicals, I guess, whether they remove chemicals or add chemicals to the environment. But why don't you go ahead and explain that for us?
Well, let me finish answering your last question, which I didn't quite completely do. Is
Okay.
that one thing is that we work collaboratively within organizations like ASTM, you just brought up, or ASHRAE, to develop standards. And our goal is really to provide the science behind those standards. So we're writing them we are not necessarily the authors. We are writing them in conjunction with industry standards, testing laboratories, and anybody actually who wants to join those organizations, industry, to create level playing field standards. And so the ASTM D8625, we sought a group of, we started off in 2021 with a group of 20 people that represented people from, the atmospheric chemists who, really know the chemistry, to the testing laboratories, to the equipment manufacturers who make the testing equipment, the analytical equipment, and then even some regulatory folks to try and get on board to develop a consensus of what the standard needed to be, what did it need to address, and how should we develop it. And after going through that process, we at NIST tested 10 air cleaners to make sure that we were creating what we call a technology agnostic standard that is not only going to work for one technology, or will do all 90%, but basically can cover all the technologies. And so that standard, one of the key goals was to have a technology agnostic standard that could evaluate chemical, related to chemical performance.
And how do you choose the chemicals? I mean, there's so many chemicals that could be, I guess.
Well, let's back up here a second.
Okay, all right.
So let's just think of, like, we have so many different air cleaners, and you can kind of classify air cleaners into two major components.
Okay.
One is passive air cleaners, and these are your traditional systems. And what I mean by passive air cleaners are systems that do not add energy or chemicals to the air. So these are things like the depth filter you would buy at the Home Depot or whatever for your HVAC system, or a carbon absorbent material that could also be impregnated on that filter. So these are things that aren't additive. And so the second type of air cleaners we have out there are what I call additive air cleaners. And these add either energy or chemistry to try and change the indoor space in a theoretically beneficial manner. So these are things like ionizers, which provide energy to charge all the particles in the space and have those particles eventually stick together and either fall out or be pulled out by a mechanical filter. Or electrostatic precipitators, which are basically the same thing, but now we have a charge plate where those charged particles can stick to. Or we also have things like germicidal UV ultraviolet radiation, where we do things like we put in wavelengths of 222 nanometers or 254 nanometers in hopes that we inactivate biological components. And this can be within a portable device, or this could be directly into the room. So those are all forms of adding energy to the space. Another thing that we can do is we can add chemistry. So we can do things like photochemical oxidation, where we shine light at what's it called? At a surface that basically creates an environment that will oxidize chemicals as it comes up over it. We can do things like add vaporized hydrogen peroxide to this space, or add ozone, or add hydroxyl radicals. And note, you should not be present when you're doing those last three things in the room. You don't want to be breathing in hydroxyl radicals. But those are all things where we have chemicals in the space. And so when we think about trying to create a test method that can deal with all of these technologies, we need to think about all the different chemistry that's happening. Even before that, we can back up a second and we can say, when we start to develop a method, we really have to think about a couple of key components. And the first thing is a method fit for regulatory purpose? And this is a big one, because it really goes to what are you developing the method for? So when I describe a method as fit for regulatory purpose, this requires a testing lab to follow the exact same procedure to determine the same result for the same specific parameter. So this is much like when you make chocolate chip cookies. You need to follow, if you want to get that chewy chocolate chip cookie at the end, you need to follow the exact recipe you see on that bag to get the cookie at the end. And everybody theoretically will get an edible cookie at the end. Now, if you're a little weird and you want to throw sand in instead of sugar, you're not going to get the same cookie at the end. So the fit for regulatory purpose are methods where you have to follow that procedure exactly, and everyone will get the exact same result at the end. And this allows external test bodies to set limits based on that test method. And so some examples of this would be like UL 867, which tests for ozone emissions, and they allow us to regulate air cleaners based on the amount of ozone they're producing, or AHAM AC1, which tests for particle removal rate through the clean air delivery rate, or the CADR. And that's used by Department of Energy to regulate the energy use per performance per clean air delivery rate. So those are methods where I say they're fit for regulatory purpose. Then there's other methods that are not necessarily fit for regulatory purpose, but may have another purpose. And these are methods where we allow people to do what they want to still test the general environment. So this would be like, you're making the cookie, but I want to add a little extra flour, or I want to add a little more baking soda, or I want to do something else to get a little fluffier cookie, or whatever. And this the analogy here would be, say somebody wants to look at how well their air cleaner removes acetaldehyde, or how well their cleaner does with methylene chloride. In a specific use case may be there that somebody wants to look at the cleaner delivery rate for a specific chemical. But not everybody's testing for that, and the test method doesn't call for that specific. Everybody has to do that specific chemical. So there's test methods out there that allow you to do these things. And it allows, if you have methods like this, an example would be AHAM AC4, which allows you to pick and choose some of these chemicals you would test for. And the reason we have these are so like external bodies could, in theory, say, go use AC4, but you should test for these chemicals because we think these chemicals are important. So that's the first divider when you're starting to develop a method, how you choose. The next real thing that we're talking about air cleaners, we got to be aware that where there's 3 different aspects that we're talking about in the indoor space. We could talk about test methods that remove particles. Air cleaners for their particle removal performance. We could talk about their chemical performance, whether they're generating or removing chemicals. And we can also talk about their biological efficacy or removal performance. And so the next step you have to take is, what are we going to do as far as what are we targeting here as far as our test method? And then you have to think about, how is your test method going to represent reality? Because we have millions and millions of spaces out there. And when you start putting those millions of spaces on top of the tens of thousands of different chemicals that could be in those spaces, and the tens of thousands of different use cases we may have in those spaces, how do we decide what is really a fair evaluation of these products that could, in theory, be placed in all these different places? And so we have to come up with an idea of what is fair and representative to give us the best idea of what's going to happen in reality. We could challenge, and this gets us to the next thing where we talk about, do we do a single pass or do we look at the performance in the room? So a single pass test would be like ASHRAE 52.2, where they look at how much particles are going through a filter, and you literally calculate the efficiency of particles on one side versus particles on the other side. And that looks at how that performance happens in that little space. But when we have air cleaners in a space, we know that the air cleaners, what we really care about is the air in the room. We don't really care about what's coming out of that air cleaner. We care about what's happening in the whole space. And so when you start talking about that, and we start talking about portable or in-room air cleaners, we have to talk about not only efficiency of the equipment, but also the flow of the equipment. Because I can have a little tiny handheld, air cleaner that produces 1 CFM and put it in an airplane hangar, and I'm going to have no effect. Likewise, I can have a jet engine, I can bring it into this office, and I'm going to have a huge effect. And so when we talk about standards, we need to decide, are we just going to look at the efficiency of the equipment or the actual efficacy of the whole unit when it's placed in a space? And then we can keep going. I mean, we can talk about, whether it's a static test, a dynamic test, whether we use realistic concentrations, high concentrations. We use, single chemical, multiple chemical, where we're looking for the removal rate, the emission rate, or we're looking at concentrations or secondary chemistry, where we're looking at a commercial system, a residential system. Does it move air or not? GUV devices don't move air. Are we looking at in-duct, out-of-duct? So we had to think about all of those things to try and come up with a test method. And we need to, when we talk about test methods, we can talk about chemical test methods, and there's 8 or 9 or 10 different ones, and they all address different things. So when we developed 8625, our goal for 8625 was 1, technology agnostic. That was one of our primary goals. 2, we wanted realistic concentrations. And this is really important when we start talking about chemistry. So 8625 is evaluates chemistry of in-room air cleaners. And so we're not looking at particles, we're not looking at biologicals, we're zoomed in on the chemistry portion. We also wanted to zoom in on the secondary chemistry. So our goal with 8625 was to say, we're going to look at the secondary chemistry related to air cleaners. And that's what kind of differentiates it with other test standards out there. And to look at secondary chemistry, it's really important that we have realistic concentrations. So it's important that we have the best we can represent the real world. And so to do that, we need to have concentrations that are the similar ratios as you would see in the real world. Because if you remember your basic chemistry, you remember if you have A plus B going to C, if I have huge amounts of A, I'm going to have a different chemistry going A to B to C than if I have very little of A and huge amounts of B. So I need to have ratios of A to B that are realistic in the real world, so that the chemistry I'm seeing in my test method is going to be similar to the chemistry I see in the real world. I know I've gone all over the place, so we'll go ahead and get me back on track.
Wow, that's yeah, there's a lot there, a lot to unpack. Let's start with this. You're looking at the chemistry, etc. What about other variables such as noise? You know, is the positioning of the filter or the positioning of the inlet to the filtration system? Are there other standards that look at that, or is that part of the? It's not. I wouldn't imagine it's part of D8625.
So we don't measure noise in D8625. Several other standards do measure noise. I can't remember them off the top of my head, but that is a key aspect about in-room air cleaners is they get turned off or turned down if they generate a lot of noise. So just from a performance standpoint, air cleaners don't clean air if they're not on. And so, yes, noise is very important. Within 8625, the standard that we're talking about here, that is not part of the standard. As far as the airflow coming out of them, maximizing our airflow per noise is the bottom line of what we're trying to do. As far as where the airflow goes, I think that's where you're kind of getting part of that question.
Yes.
Does the airflow direction matter that much? I'll back up and say that as humans, our senses are not really what we think they are. Because I know this question comes from, I see the air cleaner over there in the corner and I'm not feeling anything. How is it impacting me? That's where the question originates. It's a great question. But I would challenge people to take their fingers and touch the metal of the chair they're sitting on, or metal somewhere around them on a desk, and then touch the top of your desk and ask yourself which one of those is colder. And what you'll come up with, invariably, everyone will say the metal is colder. But if they've both been in the room for an unlimited time and the room's been relatively calm, they're actually the same temperature. And what you're measuring is the energy difference between the energy flowing out of your fingers. And it flows a lot easier, it conducts a lot easier into the metal. And so our senses, even though we think we're measuring temperature when we touch things, we're really measuring something else. And airflow is kind of the same thing. We don't have the ability as humans, despite our thinking we do, to feel airflow. We can feel airflow down to about 0.1 meters per second. Below that, air still moves. We just don't feel it. So let's put a framework on 0.1 meters per second. That means 10 centimeters per second. That means in 1 minute, you have air that can move, 6 meters, 30 feet. So basically from one side of the room to the other side of the room, the air can move, even though you're not feeling it.
In 1 minute?
In 1 minute, yeah.
Okay.
So your air is moving all the time. And so if you have an air cleaner somewhere in a space that's like a typical office size, likely it's going to be pretty well mixed in the time frame of minutes. Seconds, no. If somebody coughs in your face, an air cleaner is not going to do you any good. Doesn't matter what type of air cleaner, even sheet UV. But on a minutes to hours time scale, that space is going to become fairly well mixed. The caveats here are like, if I have an office partition, I'm not going to be able to get the air around that very easily. It's just like if you're in a bathtub and you put a divider in the bathtub and you splash on one side, it's going to be reduced on the other side. So air cleaners generally in the bake space are going to be pretty good. If you have them, behind a wall or behind a partition or something like that, they may not be able to be as effective.
Have you found any difference between air cleaners in terms of, these air intakes? Some of these air cleaners are circular, they're going to pull in air from 360, and some of them are a box, and, the air cleaner's got to be in one side, and if that side
as long as
faces
you're
the
not
wall.
blocking the flow, I don't see that there'd be a big change.
No?
Yeah,
Okay.
in the time scale of minutes. Again, in the time
Okay.
scale of minutes, you're going to be fairly well mixed. If the air cleaner is sized appropriately to your space, that's the caveat.
Okay.
So this is a really fundamental thing for consumers. Is there's three components of working in airflow for an air filter. You want it to have be very efficient, so remove as much of the thing that you're concerned about as possible. So these are when you want things that have high efficiency that can be represented by cleaner delivery rate and flow ratios. You want to make sure there's no leaks, so when you replace your air filter that there's no leaks on it. And then flow is critical, and that it has to be on. Oftentimes you go into classrooms and they're turned off because the noise is too loud. Or B, the flow ratio to the space has to be appropriate. So again, if you have a little tiny thing in an airplane hangar, it's not going to do anything. And so generally what people use is the AHAM's 2/3 rule. And AHAM is American Homeowners.
Right.
American
Home
Association Manufacturers.
Manufacturers, right.
Something like, I apologize, Randy Cooper.
Home appliance manufacturer.
Thank you. I apologize, Randy. So their rule is, which I both really like and really hate because of the units. The units don't work out, and it does not work for metric. But their rule is the clean air delivery rate, which is measured in cubic feet per minute, should be at least 2/3 the square footage of the space you put it in. And so if you have a unit that has a 400 CFM, then you should put it in, let's say 300 CFM, you should put it in a room that has 200 square feet. Now, one of the interesting things that we've discovered when looking at some of the performance of these WUI devices, not discovered, sorry, re-emphasized, is that that's really that rule of thumb, the 2/3 rule, works really well for if you have it, say, in a bedroom and you close the door every night. But if you leave your door open and your HVAC is running, that's not going to work very well because it's really mixing the entire house or the entire space between closed doors. So we did a test in one of our test houses where we had the 2/3 rule where we had 4 air cleaners throughout the entire house, and it performed just as the 2/3 rule would expect. And then we did 1 air cleaner and we sized it just to the bedroom like a consumer might do, but left the door open and let the HVAC run. And that air cleaner not only didn't perform as expected, the cleaner delivery rate that we measured not only was lower than you measure in the lab, it was 4 times lower because of all the effects of mixing of air going in and out of that room via the HVAC system and the open door. So wow. Flow is really important for a consumer, making sure that we have them sized to the right space and we have that space well defined. So when you're thinking about using the 2/3 rule, think about it in the space between the closed doors that you're going to place that device.
Yeah, that's fascinating because it brings up a quandary for people. Now I close the door and my carbon dioxide is building up in that space. Yep. Interesting. Let's go to halftime, Grayson. We'll be back. When we come back, we've got some great questions in the text, in the chat. And I've also got some kind of like speed questions I want to go through the chat GPT gave me. I think that'll help with a lot of the flows we go through the second half. Let's go, Grayson. IAQ Radio's marquee sponsor is the Institute for Inspection, Cleaning, and Restoration Certification, IICRC, a nonprofit standards development and certifying body for the cleaning and restoration industry at iicrc.org. Association sponsors are the Environmental Information Association. EIA's multidisciplinary membership collects, generates, and disseminates information concerning environmental and occupational health hazards in the built environment at EIA-USA.org. The IICRC, a nonprofit standards development and certifying body for the cleaning and restoration industry, IICRC.org. The Restoration Industry Association, the oldest and largest nonprofit professional trade association dedicated to providing leadership and promoting best practices through advocacy, standards, and professional qualifications for the restoration industry at restorationindustry.org. Industry sponsors are Particles Plus, feature-rich particle counters and air quality instrumentation. Count on us, particlesplus.com. Tramex Meters, innovation in moisture detection and humidity monitoring systems since 1974 at tramexmeters.com. EMSL Analytical Inc., providing high-quality, full-service laboratory services since 1981. EMSL.com. All right, we're back with Dr. Dustin Poppendieck. Listen, Doc, we've got a couple in the chat real quick. Absorption filters like carbon add contaminants to air when they're overloaded. Do the standards you're helping develop evaluate this where applicable?
No.
Okay. And
That's the short answer. The long answer is that coming up with a test standard for aged filters is very difficult, because it's very difficult to come up with a test aging procedure that is going to challenge each technology in a uniform way without biasing it towards one thing or another. But what the question asked is definitely true. And a classic case that you'll see this is after wildfires. High concentrations of things after wildfires, and then you leave that filter on, and suddenly the incoming air is cleaner than the outcoming air as things start to absorb off of it.
Interesting.
So it's a good practice if you have the ability and funds to replace your cleaners after a significant wildfire event.
All right. How about with respect to ozone generators, ozone generation by air cleaners? Warnings have focused on major emissions and testing reference to compliance with EPA standards. Manufacturers now promote other devices as ozone free. Aren't there still systems being sold that generate trace levels of ozone?
That's a rabbit hole. So currently, there is no EPA regulation for ozone generation. The ozone generation regulations reside within the state of California, which are regulated under regulation AB 2276, if I'm not mistaken. That regulation points to UL 867, which is a test method that's currently under revision. But UL 867 has a set of test procedures that says that if you run this test procedure, you must, and you want to be certified to sell an air cleaner in California, it must produce less than 50 parts per billion in this test procedure. Now, there's a lot of issues with that. Hopefully that is going to be revised shortly within the next couple of years. I'm on the committee to do that. UL 2998, the CARB 2287 also points to UL 2998. And if you want to sell a air cleaner that's certified as low emission, you must meet UL 2998. UL 2998 actually is actually the same test as 867, but it says you must run the experiment with no more than 5 parts per billion of ozone. And if you look at the details of the method, in theory, it's saying that you're producing no ozone, but you can produce up to 5 parts per billion under that ozone test method. And if you back calculate doing the mathematics on it, you can determine that equates to about 350 to 400 micrograms per hour of ozone. So even though a device may be labeled as no emitting ozone because that's what the regulation allows, it could still emit 350 to 400 micrograms per ozone. And that's one of the things that we're trying to get back to is clarify some of these issues.
Okay.
So if you're sold in the US and you see a device that says it's certified as not emitting ozone, it means that under the UL 867 test, it produced less than 5 parts per billion of ozone. So in theory, can produce some ozone, small amounts of ozone, but not be produce small amounts of ozone, but fairly small amounts. Does that answer the question completely?
I think so. I think you anticipated the rest of the question too. What about ionizers or photocatalytic oxidation systems? What kind of byproducts do they produce, and what type of standard measures these byproducts?
So that's a great transition into our standard. And so they, depending on the technology and depending on if they're paired with activated carbon or other things, they definitely can produce byproducts. So in the development of ASTM D8625, we actually tested 10 different air cleaners. One which was photocatalytic oxidation, one was electrostatic precipitator, one was an ionizer, and these were just off-the-shelf devices. And we demonstrated that all of them produce some level of byproducts when we challenged them. So let me go to a slight diversion. I'm going to talk about 867 just for a second to kind of set up how we go about testing these. So what we do with with ASTM D8625 is we take the air cleaner and we put it in a chamber. And that chamber is what we call a static chamber, meaning there's no flow through it. And at the very start of the experiment, we put in ozone and we put in 5 different chemicals that were selected based on their reactivity with various indoor oxidants, including ozone, hydroxyl radicals, and nitric radical. And we allow that chemistry to start. We allow those things to actually create a whole bunch of byproducts before we even start turning the air cleaner on. So we're trying to represent the indoor space as best as possible. As I said before, we're doing that at ambient concentrations. These are not really elevated concentrations to make the analytical easier. These are typical indoor concentrations. So we have that chemistry started. And then we go and we challenge the air cleaner. We run it for 4 hours and we see all the different byproducts that may be formed. And we have a paper on that demonstrates, you know, formaldehyde is generated by many of these different things. Aldehydes are generated by some. And I don't want to say that the ones that we tested are representative of all technology, all the devices of a certain technology. So, you know, even though we tested an electrostatic precipitator that actually reduced the total number of chemicals in the space over those 4 hours, that doesn't mean all electrostatic precipitators will do that. Likewise, photochemical oxidation produce formaldehyde. That doesn't mean all photochemical oxidations will produce formaldehyde. But we have now a standard that allows us to look at the end of the 4 hours. What the standard does is it kind of summarizes what the chemistry is going to happen. So we have this cascade of chemistry that's happening within the space, and the air cleaner may impact it. And at one end, on the light end of the chemistry, the end product tends to be formaldehyde. So things get smaller and smaller and smaller until all these organic molecules end up as reaction products of formaldehyde. And on the other side, as things get heavier and heavier and heavier, they start to stick together and condense, and they start forming ultrafine particles. And so the way that the standard method tries to quantify this chemistry is we look at 3 different things as byproducts to do the secondary chemistry. The first one is the formaldehyde on the light end. The second is ultrafine particles on the heavy end. And the third one is ozone. And of all the technologies we developed, we analyzed, only one did all 3. Only one of the technologies generated all 3 of that, and that was germicidal ultraviolet 222 nanometer devices. And we did a whole year study on how all that, but that's a different discussion. But that's the approach that we use to try and use this new method to try and capture the chemistry that's related to all these devices. And hopefully in the future, there'll be some regulatory agencies that's able to point to this and say, hey, test your device with this method, and you'll be able to get some kind of sense of whether or not it impacts the indoor chemistry.
All right. Cliff, I want to make sure if you want to jump in, if you have a question. I was going to ask the hydroxyl radical question there because earlier, I think, I don't remember exactly what you said, but basically,
I wrote it down. He said that if any of these were operating in the room, you shouldn't be in there.
Exactly. You should not be in there. And our audience, a lot of them are restoration contractors who are sold these products and told they can be in the room while these hydroxyl generators are working on usually odor removal. Does that make sense to you?
I mean, hydroxyl radicals are nature's vacuum. They will react with anything. That is what they do. That is what they're made for, is just to react with anything. It doesn't even have to have a double bond. It'll just react. So if it's reacting with anything in the air, It's also going to react to anything in your lungs. And so I personally wouldn't want to be going into a space that had elevated hydroxyl radicals in them, because I don't want to breathe that in. And that goes for all the oxidants. And at high concentrations, you don't want to be breathing in high concentration of oxygen. Not oxygen, sorry, of ozone or any of the oxidants, because you threaten to there's a whole industry in food of selling antioxidants. And we're now bringing and inhaling all these oxidants into our lungs. So no, I would not advise being in a space where you're using these technologies to create chemistry to your advantage. While that chemistry is there, I would not be in the space. I would advise you.
What about the devices that claim these combinations of chemicals? Like it produces ozone, it produces hydroxyl, it produces vapor phase peroxide. It's all the same device, and I think there's no filtration whatsoever, no carbon or whatever. It would seem to me that they've got some crazy stuff going on, and you don't know what's going to happen.
I think you summarized it up.
Okay.
Chemistry happens,
Right.
The thing is, we're putting in an oxidant into a whole bunch of millions of different spaces where we have not characterized all that chemistry, and we physically can't characterize all that chemistry. The best we can do is estimate that what that chemistry is using these test methods, and whether it's going to be good or bad is really hard to say. But we can quantify using these test methods of whether it's going to happen significantly or not. And I would argue we probably want to, in spaces that are occupied, not be having that chemistry being significant.
And I want to get back to the low-level ozone emitters. These still impact air chemistry, I'm assuming. Should they maybe be labeled as ozone generators and differentiated from systems that do not generate ozone?
I will leave that up to the regulatory bodies to decide.
Understood. Very well, very well done. Let's talk about UV and UV systems. They're a little different in that they're trying to deactivate, I think, as opposed to clean the air. Talk to us a little bit about these systems, and for instance, do they help reduce fungi in indoor environments? Do they help with mold growth? And also, how does relative humidity affect these air cleaners that we're talking about?
So let's be clear that we're talking about in-room UV devices where the light is escaping the actual device we have. So the light is being projected into the space, because we do have devices that use UV light within a portable air cleaner, either to inactivate the same mechanism or to activate the catalytic reactions for like a photochemical oxidation system. So we're talking about these in-room devices. We have two major categories that are marketed products right now, and they focus on wavelength 254 and wavelength 222. 254 has been historically used all the way back to the 1950s to things like reducing tuberculosis transmission. It started getting even more widespread applications. In fact, we have them in all of our regional airports. If you go to DCA or the Dulles Airport, you will see the light. If you look up, you'll see the light purple glow on some of these devices as they spread horizontally. So 254 is not safe for humans' eyes and skin, which has somewhat limited its application. So we have to use them in upper room scenarios. As such, you have to move the air up to get the inactivation to happen. And so there's a limit to how effective they can be, but they are demonstrated to inactivate viruses at the energy levels they're putting in. They do have the potential to impact chemistry, because what happens at the 254 wavelength is we can actually break apart ozone and form NOx radicals. And that NOx radical has potential to form chemistry. And we saw that chemistry happening in our chamber test when we went to our field test, where we actually tested the GUV devices in one of our restrooms here on campus, where we had lots of odors from urinal pads. We didn't actually see that chemistry. So, 254 has the ability to create some indoor chemistry, but it's been widely applicable. It's been historically applied in indoor spaces, and more recently it's been applied much more. 222 nanometer devices are relatively new. These devices operate at a higher frequency. And what happens is at the 222 nanometer wavelength, it doesn't impact our eyes and our skin to the same degree. There's lots of studies that say it's safe. I'm not a fair evaluator of those studies. But we do know when we get below 242 nanometers, we start to create ozone when that wavelength hits oxygen and breaks the oxygen apart. And the oxygen now reacts with and forms ozone in the space. And so we've demonstrated that 222 nanometers, if there's enough intensity, will create ozone. Now that ozone will react and create all the chemistry we just talked about. But the 222 nanometers also has issues. But it's great because we can now shine it directly over your conference table. You can mount it on the ceiling right above you and be in this cone of GUV light. As I said before, it's not going to inactivate the cough from the person across from you, but it will overall affect the room a lot more because we no longer have to move the air up to the ceiling. So it's able to inactivate at a higher rate because it's all the air around us. There's a couple of key things with light in general, GUV light in general. It has to have you have to have line of sight. It doesn't create ozone if you shine it right at the wall, it's not going to create ozone because there's no space for it to actually interact with the air. Likewise, it won't inactivate things if you can't visibly have a direct line of sight to that space. So if you have mold growing behind like a cabinet where we have condensation or something, it's not going to affect that because the GUV light's not going to get back there. The other thing is 254 is good at penetrating skin, and so that means it's also good at penetrating biolayers, like mold. So if you have 254 light and the mold happens to be in that one corner that it's hitting, it'll probably inactivate it pretty well. 222, however, has issues penetrating skin. We know that because it's safe. So if you have a biofilm on a surface and you're trying to inactivate it with 222, it may not penetrate very far and actually inactivate what you're interested on surfaces. So 222 is more of an airborne targeted situation as opposed to a surface targeted, just because it just can't penetrate that far. Likewise, when we have lots of humidity, the humidity starts to interact with the wavelengths. And so as you get higher and higher humidities, the inactivation rates start to drop for some microbes. Again, I'm not a microbial expert, but we do see the efficacy for some organisms drop as we start getting higher and higher above 60% relative humidity.
Okay, above 60, more into 60,
Yeah,
70, 80%.
Yeah, when you start getting those levels. So if you can keep your room at the 50% range, you're probably okay as far as inactivation.
Now, when you said that it probably wouldn't help with someone if they coughed, right across the table from me, is that because of the shielding of UV pathogens inside a droplet of respiratory fluid? I'm trying to get
That's a whole other
question.
issue.
That's another issue.
That's a whole other issue I didn't discuss. That yes, that is one of the issues with the test methods for biological inactivation is that whole issue of do we test in a pure liquid? Do we test in a simulated saliva? What do we test in for inactivation in the airborne phase? But the issue with 222 and coughing is the time it takes to inactivate a virus is longer than it takes for the cough to reach across the room.
Okay.
So it takes multiple seconds, tens of seconds to inactivate that virus, where the cough can go from the jet from my mouth to your mouth when you're sitting across the table can be less than a second. And so it's just a time issue that, you're not going to inactivate the cough, but that big splatter around you that now is hovering on you like Pigpen in Charlie Brown, you're now starting to impact that Pigpen effect and trying to lower that all the surrounding air that's hovering around you.
Okay, let's go to the roundup.
It won't necessarily eliminate is the point, and that's pretty much true with any air cleaner. Any air cleaner is never going to reduce the transmission directly from my mouth to your mouth. Only way we're going to do that is with masks.
Okay.
But it will reduce the background concentration and can reduce our risk significantly if we're not getting coughed in our mouths.
So that layered approach is important still.
Yeah.
All right, let's go to the roundup, Grace. All right, the roundup brought to us by Tramex Meters at tramexmeters.com. Cliff, let me give you a shot at a last question or two here before we have to wrap it up.
Okay. I just have, I guess, a question and comment on in ductwork UV systems. Yeah, I guess number one, I've encountered situations where odors were caused by placement of UV systems inside of ductwork, I think due to degradation of some of the materials that were inside. And the second thing I was very surprised of is I found a paper that came out of Canada put together by a UV manufacturer, and I think it was published in an ASHRAE journal about the relation, I guess, that UV light, whichever one they sold, was reacting with human skin particles inside of a house and producing odors. And not sure whether you've encountered that or would comment on it.
Interesting cases. We are doing some research right now where we're looking at 254 light and reacting with plastics. We're not doing rubber,
Okay.
but that definitely is a case study that I know there's some research on. I just don't know it off the top of my head.
Gotcha.
It definitely can happen. 254 penetrates deeper than 222, so I would expect it to happen with 254 wavelengths more than 222 in ducts. What was the second part of it? I'm sorry.
Well, I guess one was degradation, and I guess the second part was this odor, just UV reacting with skin. You know, I guess dead skin particles.
If it's 222, it can create ozone, and ozone definitely will react with the squalenes and skin particles, and that will definitely form things like 6-MHO and things like that. So if we're going that route, we definitely would see some kind of secondary chemistry if there's enough ozone present. The question then becomes, whenever we're talking about 222, yeah, are we putting in enough to have an actual significant impact on the indoor space? Yes, it's measurable. Is it significant? And that's where we are within the 222 world right now. Is we need to make sure that the fluence rates that we put into these spaces are low enough that the indoor air quality impacts are also low. Because if we put in too much fluence, too much 222 in there, the fluence rate are too high, we're going to have significant ozone impacts. But there might be this happy spot where we put in just enough to kill things, but not enough to have too much ozone chemistry initiated.
Okay,
that's where we're at with the 222.
Thank you.
Now, before we go, this is very confusing for even people who are in indoor environmental quality, okay? And I can imagine for consumers, it's even tougher. What points would you recommend consumers check before buying any of these systems being sold to them, whether it's a homeowner or a building owner or whomever it may be?
So, yeah, it's a great way to end. I think the first thing is you want to make sure you size it properly. So look at the AHAM 2/3 rule and think about the space you're going to put in it, how you're going to operate it. If you're going to have your home with the doors open all the time, you may need 4 air cleaners to have the impact that you're looking for. If you're looking just to reduce the concentration in your bedroom and you keep the door closed, you may be able to size a much smaller one. I'd also say that you want to look for one that has low noise. And so look at the lowest noise rating, because if it's not on, it's not going to do anything. The next thing you also want to look at is realize that the clean air delivery rate is at the highest setting. And so if you're buying a unit that claims a clean air delivery rate of 300 and you operate it on the lowest setting, the clean air delivery rate may only be 100. And so if you really want that performance, you have to operate at the highest per setting. So it might behoove you to either buy one with a bigger clean air delivery rate that you want, so you can operate at a lower setting with a lower fan speed, or to buy multiple smaller units that add up to the total clean air delivery rate that you're looking for. But I would get back to the key points of an air cleaner is it has to, fit, flow, and efficiency. So the efficiency is a high clean air delivery rate number. Make sure every time you replace that filter, there's no leaks when you put that new filter in, and then it has to be on to be good to work. It's not on, it's not going to clean the air.
I think that's a good way to wrap things up, but let's also ask before we go if there's anything we missed that you'd like to add or any final thoughts.
I think that was the main final thought is make sure you size it properly and make sure that you keep it on. If it's not on, it's not going to work.
There is one other question I wanted to ask, and that is what current up and coming technologies, do you see anything that kind of piques your interest that you think maybe we should be watching for?
I wouldn't say it's new technology. I would say it's new application. I studied vaporized hydrogen peroxide back in 2002 when we were trying to eliminate anthrax spores. And I know it's being touted in the cleaning industry to a greater and greater extent. And as long as we're using it safely and we're not in the space when we're using it, I think it has potential to, based on my experience 20 plus years ago, to create less byproducts. And I'm really concerned about secondary chemistry than compared to some of the other remediation technologies we work with. Now, granted, it has a whole bunch of other balls of, there's a whole bunch of other problems with VHP that we got to think about, including, potentially creating mold environments if we don't dry spaces dry enough after using it and things like that. But it seems to be, it has potential, but I also would be caution in using it, and I don't think it's been researched to the extent, say, ozone devices have.
All right. Well, thank you so much, Dr. Dustin Poppendieck, for joining us today from NIST. We talked about evaluating air cleaner technologies. Before we go, I want to thank the Z-Man, my co-host, of course, Grayson Gone Fishing Fisher at the controls. Most importantly, our audience and our sponsors. We'll be back in 2 weeks with the next episode of IAQ Radio Plus.
For IAQ Radio, I'm Spike Reel saying thanks for listening.